So now to wrap up our discussion of LTI systems, let's look at how the impulse response can tell us properties of the system. So remember, we're looking at signal properties of h of t, the impulse response. How do those translate into system properties? Of our underlying, of our LTI system, right? So that's what we want to be able to answer. And so now, for the first one, let's look at causality. So we'd like to be able to show that the support of the impulse function, that is where the impulse function is non-zero, actually determines the temporal dependence of the output on the input. And then with this, we can use delay and truncation to approximate a non-causal system with a causal system. Like, for example, you might have a system that you'd like to implement, but it's not causal, but you could sort of approximate it by kind of shifting it over and truncating it. And we'll see what that means. So LTI systems are already linear and time invariant. So we're really actually interested in causality, stability, and invertibility, and that's the topic of the next few videos. So remember our important fact from continuous time and discrete time LTI systems is that the impulse response contains everything you need to know about the system. In particular, we should be able to determine these properties, causality, stability, and invertibility, from the impulse response. So now we'll look at to see how to use the impulse response to figure out whether the LTI system is causal, stable, or invertible. And for this particular video, we're going to focus on causality. Okay, so we're going to treat continuous time and discrete time kind of in parallel with each other because the things we're looking for in the impulse response are essentially the same. So to determine if a system is causal, we can look at the convolution formula. So here's our definition of convolution for continuous time and our convolution for discrete time. So if y of t at time t, like t equals 5, or n equals 5, if we want it to depend only on past or current values, that's what the definition of causality means. It means that I'm only using the past or the current input to determine the output. Then basically, h of t minus tau, this is x of t delayed by tau. So if I want to make sure that what's inside here doesn't get bigger than t, which means that I need no negative tau. And similarly over here, if I want y of n to depend only on past values, this k here can only be negative, or cannot be negative, right? So that is, we don't want, if k is negative, then this thing starts becoming like, if k is -1, this thing starts becoming n plus 1, and suddenly you have yn depends on xn plus 1. You don't want that. And the only control you have over this thing is to make the h of t zero that out. So that is, for those values of tau, or k, you need h of t to be 0, and h of k to be 0. So we can simplify, in this case, our convolution formulas. They can't depend on negative k or on negative tau. So this means that the impulse response h of t should be 0 for t less than 0, and h of n should be 0 for n less than 0. So essentially that means like we're multiplying by a unit step. But I think the easiest thing to do is to think about this graphically. So what we've shown that is that h of t has to be equal 0 for t less than 0, and h of n has to be 0 for n less than 0. And this implies that the system is causal. And it helps to think about this in terms of a picture. So this system is causal because all of this stuff is 0. And this thing is not causal. It's neither causal nor anti-causal, actually, because there's some parts that here that are involving negative time, and that if you think about it, that means that when I do the flip and slide, I'm actually using some of the future inputs to determine the system output. In discrete time, it looks the same. So this is causal because all this stuff is 0. This is great. It's all 0. But since these things are non-zero, this makes the second system non-causal. Okay, what about anti-causal systems? Well, we get actually the exact reverse. So if you have an anti-causal system, h of t has to be equal 0 for t greater than 0, and h of n has to be 0 for n greater than 0. And these imply that the system is anti-causal. So this thing is causal because all this stuff is 0, and this thing is anti-causal because all this stuff is 0. So really it just has to, you just plot h of t, and you kind of look at it and you say, oh, well, where is it equal to 0? And then that'll tell you whether it's causal, anti-causal, or neither causal nor anti-causal. And the same thing holds for discrete time. Again, if the impulse response is 0 for n less than 0, then it's causal. And if it's 0 for n greater than 0, then it's anti-causal. Okay, what about memorylessness? That was a very special case where the system is both causal and anti-causal, in which case you've cut out t greater than 0 and t less than 0, or n greater than 0 and n less than 0, so the only thing left is that you have something at 0. So for CT systems, the output y of t has to be a function of x of t only, and the only way that you can have that is that h of tau is just the delta function with some gain a. So this is just a system with a gain of a. This is the only memoryless system. And similarly for discrete time, you have that the output, the impulse response has to be just a times delta of k, and that's also just a gain of a. And so again, it's really important to think that the gain, simple gain, is the only memoryless system that's out there, LTI system that's out there. Okay, so why do we care about causal and non-causal systems? We talked about this a little bit before, but just to sort of re-emphasize, causal systems can operate in real time. So to compute the output of a system, you just need the current and past values of the input signal x. So you can have like a memory in your implementation. You can have a memory which kind of remembers the last part of the signal and stores it, and then you can use that to compute the system output. So that's really important for online signal processing and filtering, for things like control applications, radio transmission, doing live audio effects. If you're watching a concert or something like that, things like vocoding and auto-tune have to work in real time in order to sound like it's following the music. Non-causal systems, of course, can use past and future inputs. So this is really useful when you're doing offline signal processing and filtering, in particular looking at things like images or looking at video. If you want to do some post-production work in audio, for those of you who are kind of interested in studio processing effects, all of those things you can use non-causal systems, which is a much bigger class of systems than just the causal systems. So causality is sometimes a barrier depending on the thing you're trying to implement. So what if you have a non-causal system that works really well? Like, so you have a effect that you can get by looking at taking it on a recording of some sound, but you'd like to mimic that in a real-time processing system. So one thing you could do is, if you're willing to tolerate some delay, and again, some applications are not, you can delay the impulse response, which would delay the output of the system, and that might make things better. So let's take a look at this. So we delayed a little bit, and now we can see all this junk over here is kind of small, right? And if it's small, we can truncate it. That is, we can make all this stuff equal to 0, and that will make it the overall system causal. So you get something that looks like this, and so this is a causal approximation to h of n. And this sort of approximation that we do, we take something that's ideal or something that we would really like to be able to implement, and essentially manipulate it a little bit using some techniques to do an approximation. That's like the heart of engineering, right? Is to be able to take something ideal but not buildable and try to make something that's buildable out of it. So, as some exercise for yourself, try to look at these different impulse responses here and determine if the system is causal, anti-causal, or neither causal nor anti-causal. And again, this is really just a matter of plotting h of t and then looking to see where it's equal to 0. So hopefully this is pretty straightforward. And you can go back and look at some of the other systems that we've looked at in class. We've looked at mostly causal systems so far, but you could see, well, how would I manipulate this to make it non-causal, for example? That's a good exercise to get comfortable with this feeling of how to look at the impulse response of an LTI system and determine the causality properties.